Welcome to this week's colloquium at the School of Astrophysics. We are glad to have Dr. Lankeshwar Dey as our speaker today. So Lankeshwar did his integrated PhD from TIFR and then went to West Virginia University in the US for his first postdoc. Now he is on his second postdoc at IA 4th in Crete, Greece. Lankeshwar has a sort of underlying long-term connection with this department because he went to Krishnath College for his undergrad, where he studied with. Well, he stayed in SCM's ancestral house. So he is not only blessed by SCM and SCM's father, but also SCM's grandparents. And then he went to WVU for postdoc, where one of my PhD classmates is a faculty. And now we have a student here who got a PhD position there. So, all this connection, Lankeshwar works in gravitational waves, and now he's particularly into this gravitational wave background from supermassive black holes. And since there are many people who are interested in supermassive black holes, I mean, everyone is interested in supermassive black holes. Or black holes. So, so I'm sure that will be very interested to hear Lankeshwar, please.
Okay, yeah, thank you very much for giving me the opportunity. One thing before I start, like during my presentation, if you have any doubts or any sharp question, feel free to raise your hand and pause me, and I'll be happy to answer. Okay, so let's start. Okay, so for most of the history of astronomy, it was only about the things that we could see with our eyes. Okay, initially with our naked eyes, but after the invention of telescopes. Is it a laser pointer?
Yeah, that's the pointer. You cannot change slide.
No, that's fine. Okay, thanks.
Integration by bonds.
Okay. Yeah. So initially, it was about only the things you could see with our naked eyes. But then after the invention of telescopes, it was with the telescope. But still, our vision towards the cosmos was limited to a very small part of the whole electromagnetic spectrum, namely the visible light. Okay. But that things changed in the last 100 years, where we started observing the universe at different parts of the electromagnetic spectrum. For example, radio in 1932 to microwave to infrared, ultraviolet, X-ray to gamma rays. Okay, and interesting thing is, like, when we look at the universe at these different wavelengths, they tell us different stories about the universe. Okay, and when we combine all of them together, then we'll get a complete picture of what is happening in the universe. For example, if we look at this galaxy, which is Hercules A, if we look at the visible light, we see just like the galaxy and the visible light. If we look at the X-ray, this is how it looks. And if we look at the radio wavelength, then we see the jets. Okay, and when we combine all of them together, then we get a bigger picture. Okay, what is happening in the galaxy. So when we combine observations at different wavelengths, we see the bigger picture. Again, that's also true for our sun. Okay, even in our sun, if we observe different wavelengths, we see different aspects of sun. Like at visible, we see the photosphere. At higher wavelength, higher frequencies like UV, we see the corona, solar corona, and the solar atmosphere. If we go even higher, like X-rays, we see the solar flares. So if we don't do the multi-wavelength astronomy, if we just observe one frequency, then it's like we're blindfolded and we're trying to feel how an elephant should look like. Okay, and only through like the multi-percentage astronomy, we remove our blindfold and then we see the whole elephant and how it looks. But even with all the electromagnetic wavelengths, the blindfold is still not fully open. Why? Because it's not only electromagnetic waves. Universe has other messengers that carry information about different objects and different processes happening in our universe. For example, neutrino is one of them. So neutrinos are a very tiny chargeless particle, and also like very like mass is also very low, and they interact very weakly with all the materials. So detecting them is actually very difficult. They come in 3 different flavors: electron neutrino, muon neutrino, and tau neutrino. Okay, and although it's difficult, but we have neutrino observatories in different parts of the world. Like this is one example. This is Super Kamiokande. This is inside the observatory in Japan. Okay, so neutrino is one of them, apart from electromagnetic waves that carry information. What else? And there is cosmic ray. What is cosmic ray? Cosmic ray is highly energetic charged particles that comes outside from the our world and enters the atmosphere. And when it collides with the atmosphere particle, it creates the cosmic shower. Okay, and this is again another things that carry information. And again, here is a cosmic ray observatory in Ooty in India. It's called GRAPES. And last but not the least, there is also gravitational waves. So gravitational waves are ripples in the space-time curvature. We'll talk about this in more detail, so don't worry, we'll talk about this. And just to give an example, like I'm giving the other observatories, we have also gravitational observatories. For example, the ground-based LIGO detectors, one in Livingston and one in Hanford. Okay, so when we combine the observation from a particular things that is happening in our universe in both electromagnetic and in one of the other messengers, then we from multi-wavelength we go to multi-messenger astronomy. Okay, so we're using different messengers, electromagnetic and something else. And the supernova 1987A is the first instance of this multi-messenger astronomy, where in like February 23rd of 1987 we observed this supernova happening in Large Magellanic Cloud in optical wavelength. But 2 to 3 hours before that, it was visible in visible light, we observed a burst of neutrinos from the same source. Okay, and this is the first instance of multi-messenger astronomy where we observed neutrinos and electromagnetic waves from the same source. And just this one observation has given us lots of information about the supernova, or especially the core collapse supernova in this case. They're like, from this observation, we have confirmed that yes, the 99% of the energy of the supernova is carried away by neutrinos. And also in core collapse supernova, the optical emission arises hours later when the shock wave reaches the stellar surface. So this goes with neutrino, but now let's come to the gravitational waves. So what are gravitational waves? I guess most of you already know, but gravitational waves are ripples in the space-time, and they are created by accelerating masses, for example, black hole binary, and they're created by black hole binary, and this travels outwards with the speed of light. And how do we detect gravitational waves? We can detect gravitational waves by using the property that whenever gravitational waves pass through an object, the object gets tidally deformed. And the gravitational waves have 2 different polarization. One is plus polarization and one is cross polarization. And how the object will get deformed depends on the polarization state of the gravitational waves. So in this example, you see this animation here. If you take a ring of free floating particles, which is circular ring on the plane of this projector or this board, and if a gravitational wave passes through perpendicularly through the plane, then if the gravitational wave is plus polarized, then the circular ring will be deformed in this way. So once it will be stretched in this way and again in this way while it is squeezed in the other direction. And you can see this creates like a plus kind of pattern, and that is called the plus polarization. And if the gravitational wave is cross polarized, then the deformation will look like this. And any gravitational waves that is coming to us can be written as a combination of this plus polarization and cross polarization. Okay. And the amplitude of the gravitational wave that is creating this deformation is given by the fractional change in the length scale. Okay. So if the initial diameter was like when it is circle is d or L, and the change that is happening due to gravitational wave is delta L, then the amplitude or strain of the gravitational wave is given by the fractional change delta L by L. And the gravitational wave astronomy is a field that has started very recently, like just 10 years ago, when the LIGO detectors, 2 LIGO detectors have detected the first gravitational waves from 2 merging stellar mass black hole on 14 September 2015. And here you can see basically the strain or the amplitude of the gravitational wave, how it varies with time. And this is the signal detected by LIGO Hanford. This is by the Livingston. And you can see this matches quite well from the model predicted. Like if two black holes are merging, how the signal should look like, and what we detected is very similar. And you can here see like the frequency of the signal as a function of time. As you can see, like with time, the frequency increases. That is called the chirping. Okay, because this is like the characteristic signature of when two black holes merge, the frequency increases before they merge. So, and in 10 years, it started with just one black hole binary, but now we have more than 200 detections of gravitational waves from merging black holes or neutron stars or even black hole neutron stars. And here are all those 200s that are more than 200 actually, that was published in the Gravitational Wave Transient Catalog 4. Now probably like the number of detections is more than 200, probably close to 300. And here the y-axis is in solar mass, and all these blue circles are black holes. And you can see like this is showing two black holes merging to be like form a bigger black hole. So all these things are like black hole mergers. Here you can see few neutron star mergers, two neutron star merging and creating either a more massive neutron star or a black hole. And there are also like we have detected some EM black holes, like black holes and neutron star in EM observations, and some of them are also showed here in red and this yellow. Okay. So yeah, now it's like it's a boom in the gravitational astronomy as we are detecting many merging black holes, gravitational wave from many merging black holes and neutron stars.
LIGO, Virgo, Kagra, neutron stars.
Yes.
These are what? Neutron star binaries that were detected through GW?
Yes, like if two yellow is merging and creating this, so this is a neutron star, this is a neutron star, merging and creating. So here this is somewhere like a mass range where it is confusing whether it is a massive neutron star or it is a black hole, because we don't know what is the upper limit of the mass of a neutron star. Okay, because it depends on the neutron star equation of state. Depending on the theory, the upper limit of the mass of the neutron star can be 3 solar mass to in fact like 4 solar mass. So when two neutron star merges, let's say 1.5 solar mass, 1.5 solar mass, and creates a 3 solar mass object, it's in the confusion zone whether it is a black hole or a neutron star. So you see this like two neutron star merging and creating something. It is the color coded is like both blue and orange. So it's
that is okay, but seems that there are what, like 6-7 cases of these.
Yes.
But there is only one that is really confirmed, isn't it? I mean, there are the others?
No, like one only confirmed, but we have also seen the EM observation counterpart. But there are more confirmed neutron star mergers, but we have not seen the EM counterpart.
There are confirmed neutron star mergers, but no EM counterpart.
How do you then confirm that it's not a black hole and then
Just from the mass. Yes. Because if mass is less than 2 solar mass, then it's not a black hole. Yes. Okay. So we have already talked about this a little bit. Okay. So with gravitational wave also we can do multi-messenger astronomy. And again, the first and only instance of this happening is in 17th of August 2017, when LIGO detected a merger of two neutron stars in both LIGO Hanford and Livingston. It was not visible in Virgo, but that actually helped us to pinpoint the sky location of the source. And here you can see again the chirping of the signal as a function of time. And just 2 seconds after the merging happened, the Fermi detectors have detected GRB, okay, short gamma ray burst from the same sky location. Okay, and so again, this is the first and only instance of observing a neutron star merger in both gravitational waves and in EM wavelengths. First it started with GRB, but later it was followed up with like from all wavelengths from radio to X-ray, and lots of information we were able to learn from this. For example, yes.
Yes, question. So with GW observations, it was confirmed that these are neutron star mergers.
Yes.
But then there wasn't the electromagnetic thing that was detected. This is the only case where the electromagnetic. What was the reason for that? Could they not direct it to that part of the sky, or what was the reason?
Okay, so there are a few criteria has to be satisfied for detecting neutron star mergers in EM. Okay, so this one in particular was very nearby. It was at 40 megaparsec. Okay, so even, and it was in terms of GRB, it was not actually very bright. Okay, it was just barely visible. So if the neutron star merger happening is little farther away, then it can be like not bright enough to be visible. Second, when neutron star merger happens, okay, it creates a jet. Okay, and what we see in the EM like GRBs is the jet emission. Okay, now it depends on like the direction of the jet. If the jet is directed exactly towards us, we'll see it very bright. And even in this case, that jet was not exactly directed towards us. Okay, it was like there's some angle between them. That's why it was not very bright. But if the emitted jet is pretty far away from a line of sight, then we will be able to see this.
Because this one, the GRB 170817A.
Yes.
Sorry, the GBQ 170817. That was done in like multi-wavelength observation.
Yes.
It's not that all the observations had to be transient. I mean, even after few weeks, you actually see the glow in some of the wavelengths.
Yes.
Right? Because it's a lot of emission processes. So I'm curious that
I think what you are asking, the answer to that is just two neutron star merging is not a very bright thing. Only if there is a GRB, then it's bright.
So it's
And
not
GRB
necessary that GRBs have to be always there when two neutron stars are merging.
No, I think it's GRB is happening always, but it's the jet is not pointed towards us. Yes.
Also, what's the distance, that also matter.
Yes. So this one has like 40 megaparsec. And another thing is like for this one, luckily another thing is sky localization. Okay, like how well we can constant like which part of the sky it is coming from.
Yeah. In little above, because this EM follow-up of GW events is like people are really sitting on it and trying to do their best. So I think
Yes.
7.
In fact, it was lucky that one was detected so quickly in 2017.
Yes.
It would have been much later.
But that kilonova event also there was no GRB.
No, this is the kilonova. Like
This is the kilonova.
yeah, this is like not that bright. That's why we call it kilonova. Yeah, yeah. So another thing is like the sky localization. For this one, the sky localization was pretty good because it was very bright. The other ones, again, if you have a very large sky to cover, you don't have that enough telescope time to go through all of them. And if it is very large sky, then again your false alarm probability becomes low.
I think detected in this.
No.
Yes, please go ahead.
Okay. Any more question?
No.
Yeah, so just one multi-messenger observation of gravitational waves and in electromagnetic waves confirm many things. For example, there has been lots of theories of how GRBs are produced. It confirmed that neutron star mergers can produce short gamma ray bursts. Okay. Second thing, it also confirmed that neutron star merger creates heavy elements through our process, like gold and platinum and all those like expensive metals. And it also confirmed, we knew from theory that gravitational wave travels at the speed of light, but it again confirmed that it travels at the speed of light. And also it gave us an independent measurement of the Hubble constant. Okay, so again, as you can see, just one multi-messenger observation can give us lots of information. So multi-messenger observation is actually really important for the progress of astronomy. But just like in EM astronomy, we have a huge frequency space, right, from radio to gamma rays. Similarly, in gravitational waves also, different things, different processes in our universe can produce gravitational waves in a huge frequency range, going from like femtohertz to kilohertz. Okay, and the ground-based gravitational detectors like LIGO, Virgo, or Kagra, they can detect only a small fraction of the whole frequency range. Here in the x-axis, I am showing the frequency of the gravitational wave, and y-axis is like the strain or the amplitude of the gravitational wave. And there is the sensitivity curve for the advanced LIGO. So you can see we can only detect gravitational waves from LIGO in the frequency range of around like 10 hertz to few thousand hertz. Okay, and we can detect up to a strain of around 10 to the minus 23. So the sensitivity curve means we can detect anything, any event which has a strain within the bucket or in the upper side of the bucket above that line. Okay. Sorry?
Delta L by L.
Strain is delta L by L. Yes, like how much it will deform anything. Yes. And then we have this like future space-based gravitational observatory like LISA that is supposed to fly around 2035. And with LISA, we'll be able to detect gravitational waves with frequencies around millihertz. Okay. And then there is another one experiment happening right now called pulsar timing array. And with pulsar timing array, we can detect gravitational waves in very low frequency, in the nanohertz frequency regime. Okay. And again, in today's talk, we'll focus on this part of the low frequency gravitational waves and how we can detect low frequency gravitational waves using pulsar timing array and what can it tell us about the universe or the astrophysics that is happening. Targeted audience. Oh, okay. Yeah, okay. I'll come to that, but just to like brief answer is most probably supermassive black hole binaries, okay, but around like million to billion solar mass, 10 to the power 6 to 10 to the power 9 solar mass. Even more, like it can be 10 to the power 10 solar mass. Yes. Supermassive black holes means it has to be more than 10 to the power 6 solar mass. Yeah. No, a single supermassive black hole will not produce gravitational waves. We need, yes.
It's effectively mostly the background of supermassive black hole.
I'll come to that. Yes, I'll come to that. Yeah. Yes. Yeah.
Why all the detectors are only targeting the space diffraction? That means I will say that you say the strain is delta L by L.
Yes.
That means you are measuring the deformation in space.
Yes.
Not the time.
No, both in space and time.
No, time is not here, right? We say the space time.
No, if you think about the frequency domain.
Never time was never measured because time.
He's saying that
Oh, you are talking about
it's a different space time, but we're looking at the space deformation.
How do you see the time?
Time deformation is difficult to measure, I guess.
Actually, I mean, what you are saying, it can be different explanation of this. Okay, so that we can discuss later. It's just different explanation. For example, in PTA, what we actually measure is the time delay. Okay, yes. But that will be a like longer discussion and more explanation. Maybe we can discuss this after the talk. Okay. It's just different way of saying things, but yeah.
The GW expert in the room.
Okay. So now let us look at how pulsar timing array can detect low frequency gravitational waves, how it works. Okay. Mostly you people are familiar with how LIGO works, like with this L-shaped interferometer. Okay. But today I'll tell you how pulsar timing array works and how using pulsars we can detect low frequency gravitational waves. So as the name suggests, we use pulsars, okay? And what are pulsars? Pulsars are highly magnetized, rapidly rotating neutron stars. Okay, so I guess you are familiar with neutron stars. And what happens, like highly magnetized neutron stars, they emit beam of radiation along their magnetic axis. Okay, and if the rotation axis and the magnetic axis are not aligned, then and if our Vig geometry is in such a way that every time it rotates, the beam can cross our line of sight. Okay, and if that happens, every time the pulsar rotates, we'll see a pulse. Okay, and these are like mostly like most bright in radio frequencies. So use radio telescopes to observe these pulsars. And the interesting thing about pulsars are they are very stable rotator. Okay, so the rotation period is almost fixed. So if the rotation period is 1 second, we can expect like every 1 second we'll see a pulse. What? No, the like rotation axis is around like vertically.
It's like a lighthouse.
So let's say, yeah, it's like this is my rotation axis. Okay, I'll give you an example. Okay, people call it pulsar dance. Okay, let's say I am neutron star. Okay, and this laser light, this is my beam, and I am rotating like this. Okay, so if now you are not seeing this, but only when it comes towards you, then you see the pulse. Again, you don't see this, and again it comes to you, you see the pulse. Exactly, this is happening. Okay, so the rotation axis is fixed along this, and it's just the jet or the beam is not aligned with the rotation axis. And is it clear? Yeah, because this is not the rotation axis. This is the beam.
Till the picture seems to be it's also
This particular movie has a like seems like the sphere is actually.
Oh, okay. I see.
But that's something that.
Okay. Okay.
Yeah, go ahead.
So we use these pulsars and to detect gravitational waves. How? Because as these are very stable rotators, okay, we can create a model, okay, and with that model we can track each rotation of the pulsar, okay, and with that model we can actually predict, like if we see the first pulse or 100 pulse as this time, when we'll see the millionth pulse or even a billionth pulse, okay, so we can actually predict when a particular number of pulse will arrive at Earth, okay, and this process creating the model is called pulsar timing, okay, where we observe the pulses, we build a model to explain the pulses, and we can use the model to predict based on the model when the next pulse will arrive. Okay, and what we used millisecond pulsars. Millisecond pulsar means the pulsars which has a rotation period between 1 millisecond to roughly 20 millisecond. Why? Because the millisecond pulsars are more stable. Okay, if you see a normal pulsar which has rotation period around 1 second, they tend to have more noise, like they go through glitches and other things. But millisecond pulsars are very stable in that regard. So that's why we use millisecond pulsars for our purpose. Okay, and I said the pulsar rotation is very stable, but there are few things like the pulse is emitted from the pulsars and it is traveling through the interstellar medium. It is coming towards us, and few things can affect the arrival time of pulses because when it is traveling. Okay, and gravitational waves is among all those things. Okay, there are a few other things. For example, the ISM. Okay, the ISM is changing with time. The Earth is going around the sun. Okay, so it is also one thing we have to take care of that. So there are few things that can affect the arrival time of pulses, and gravitational waves is one of them. So how it is happening? Let's say, yeah, if there is no gravitational waves, this is how the pulses should arrive. Okay, exactly like equidistant in time. But if there is gravitational waves passing between the Earth and pulsar, then instead of this, the pulses will arrive. Sometimes they will be squeezed together, so they will come earlier than we expect, and sometimes they will be they will be stretched. Okay, and that time we will see the pulses are arriving later than when we expected. Okay, and we use this to actually measure the gravitational waves, and we're defining a term called timing residual. The timing residual is basically the actual arrival time of the pulse, like as we measure with the telescopes, minus the predicted arrival time based on our timing model.
Difference kind of thing.
Yes.
But here is the problem. We can only measure this time dilation thing in the strong field gravity, not in the weak field gravity.
No.
No.
Time dilation happen everywhere. Like at strong field, it is much more prominent, and weak field, it is much less.
Traveling towards us.
Okay, maybe we should discuss this later because I need to give it more detail. Okay. Okay. So in PTA, what we are doing, you can think of, is like in LIGO, a gravitational is coming, and we have this L-shaped arm where laser is passing through. And what ultimately we are doing, we are measuring the change in length of this arm through interferometer. And in case of PTA, you can think those mirrors at the end are basically replaced by pulsars, and those L-shaped arms are replaced through this Earth pulsar baseline. Okay, but there is one problem, right? You can ask, you said there are also other things like ISM or the motion of Earth in the sun, or even like, as I said, the pulsar rotation is very stable, but how stable? Like they also have some intrinsic noise. Okay, so how can you distinguish like the delay that is happening to the pulse, whether it is coming due to gravitational waves or for something else? Okay, how can you do that? And we can do that using something called Hillings and Downs correlations. Okay, and what is this correlation? Again, it will be easier to show through this video. See if it works. Okay, so what you can see here, for example, let's say here is the Earth, okay, and there are many pulsars in the sky which are in different directions from the Earth, okay, and we'll observe all these pulsars and we can calculate the delays that is happening to these pulses from our model, and then we can cross correlate the delays between different pulsars. And if we take two pulsars, let's say 1 and 2 here, and we measure the angle and plot the cross correlation as a function of angle between two pulsars on the sky, then if the delay is happening because of something else, like for example due to the intrinsic noise of the pulsar, it is happening because of something is happening in the ISM or something else, then we don't expect to be there any correlation, because all those are independent things, because all pulsars are independent. What the pulsar is doing, one pulsar is doing, the other pulsar doesn't know about. Okay, so the delay that is happening because of something else, there will be no cross correlation between them. So if you plot the correlation strength as a function of the sky angle, the angle in the sky between two pulsars, then it will be around 0 because no correlation.
Two pulsars for pulsar timing array setup means these are kind of setup, but this thing is replaced by two pulsars. It's like that. That concept should be.
You can, yeah. So if only two pulsar, then we cannot detect it, because it can be, the delays can be coming from different things. Again, like just give me a minute, that will be more clear.
Multiple pulses. Else you can't determine the delays.
Yeah. So without gravitational waves, there is no correlation. But if the delay is happening due to gravitational waves, then what happens? If we take two pulsars and calculate the correlation between the delay and plot as a function of the sky separation, and you get this kind of a line. Okay, what happens, like at very low separation, that is when two pulsars are around the same direction, you get a positive correlation, and as the angle increases around 90 degree, you get a negative correlation. So that means if one pulsar is here, one pulsar is in 90 degree direction, and if you calculate the cross correlation between the delays, you will get a negative correlation. And again, if we increase the pulsar separation to like 180 degree, that is the two pulsar are around opposite direction, again the correlation becomes positive. Okay, yeah. So if you observe many pulsars, and if you calculate the cross correlation between the time delays, and if it follows this curve, then we are certain the delay that is happening, causing this delay is certainly gravitational wave, not anything else. Because if there is anything else, we will not see this correlation as a function of the pulsar separation angle. So what we do, we just don't observe two pulsars, we observe lots of pulsars. Okay, and here is again a schematic showing like the pulsars we observe. Here is like a depiction of Milky Way, and the solar system is somewhere here, and we observed many pulsars around the solar system. Okay, so we create an array of pulsars, and then what we do, we try to search for this HD correlated timing delay to detect the low frequency gravitational waves. Is that clear to everyone? Question? Oh, okay. Okay, so if this part is clear, then it will be easy. So there are actually multiple pulsar timing array experiments around the world. Okay, for example, in North America we have Nanograv, which is called North American Nanohertz Observatory Gravitational Wave, and I'm a member of that collaboration, where we used to observe all the pulsars with big radio telescopes. For example, Arecibo, but unfortunately Arecibo is not there anymore. It was broken in 2020, but we are still continuing to observe using green band telescopes, VLA, and CHIME. CHIME is a telescope in Canada. And then there is European pulsar timing array, which is like collaboration between different countries in Europe, which again uses big radio telescopes like Sardinia Radio Telescope, Lowell, Nancy, and Oysterbrook. There is one in South Africa, okay, which uses the Meerkat telescope, which is a pathfinder of SK Meet, and this is called Meerkat pulsar timing array. But now it is forming a bigger collaboration called African pulsar timing array, which they are involving more countries from Africa. And there we have our own Indian pulsar timing array, which nowadays mostly uses GMRT, but earlier also used to use UT radio telescope, and UT is expected to be upgraded soon, so maybe we can use UT again. And then there is China that uses FAST, called Chinese pulsar timing array, and then in Australia we have Parkes pulsar timing array, and they mostly uses the Parkes radio telescope.
We joined South Africa and Australia.
Yeah, in Australia it's SK low. So there are two different frequency range. In Australia they are building a telescope which can go to lower frequencies, and in South Africa they are building a telescope which can go to like sort of high frequencies compared to the Australian one.
Just correct me if I'm wrong. So about how many? 25, 30 pulsars are being observed in the Milky Way?
More. Okay. So we have like more than 2,000 pulsars discovered. Okay. But to be a good quality pulsar that can be included in pulsar timing array, there are around like 120, 130 of them. But again, like all of them cannot observe all of them, because some are in the northern hemisphere that cannot observe the pulsar in the southern hemisphere. So if we combine all of them together, then there is something called international pulsar timing array, which combines all those PTAs. Then we have around 125 millisecond pulsars observed between all these PTAs.
How?
Nowadays, like around 75.
How number? There are magnitude less.
Yeah.
I was thinking 30 pulsars.
No, I mean we started small, but now Nanograv observe around 75 pulsars. Meerkat observe around 80 pulsars.
And these are all millisecond pulsars.
These are millisecond pulsars, like period less than 20 millisecond. There is one around 22 millisecond. Yeah, but it's again in the same ballpark.
There's so many.
Huh?
There's so many.
Oh no, it's the whole Europe. Yes.
European.
I mean, yes. They have like England, Germany, France, Italy, everything. Okay. So now all this experiment has been going on for more than like 15, 20 years. And have we found anything? Have we found a gravitational wave? Okay.
15, 20 years.
Yes, yes.
Even before GWS, people were just.
Yes. People have been like, even LIGO detected the gravitational waves. This experiment has been going on before that, like from around 2000 to 2005. Yes. Yes. Okay. So actually in 2023, about like around like among all those collaboration, no, individually, 4 of them actually found evidence for a gravitational background. Okay, one is Nanograv, one is EPTA and Indian pulsar timing array collaborating together, and Parkes pulsar timing array. But later also Meerkat pulsar timing array and Chinese pulsar timing array, they have also found the same thing. Okay, in their data. So what we found? We have found evidence for a low frequency gravitational background. Okay, what is the background? Means it's not like one single source. It's like the gravitational is coming from every direction. Okay, it's an isotropic background. Okay. Yeah, by background it's like by default it is stochastic. Yes. So okay. So what happens, like if there is a background, how will it manifest in a pulsar timing array? So the gravitational background manifests as a common spectrum red noise process with Hillings and down spatial correlation in pulsar residuals. So we have already talked about Hillings and down spatial correlation that you know. Okay. Now what is this common spectrum red noise process? Okay. Now maybe you know the red noise process. Red noise process is something like it's a noise process. If you take a Fourier power spectrum, then there will be more power in lower frequencies compared to the higher frequencies. So there is more power at like redder wavelengths, like higher wavelengths. That is called red noise. Okay, and what is common spectrum red noise? Common spectrum red noise means like if you have pulsar residuals, and if you take different pulsars, the residuals, and if you calculate the Fourier power spectrum, then all the residuals for all different pulsars will have the same amplitude and same spectral index. So just and give an example. Here you can see, for example, the residual in 3 different pulsars that is created by the gravitational background. Okay, and in time domain you can see they look different. Okay, but if you take a Fourier power spectrum of all these 3, you will get the same. At low frequency the amplitude will be higher, at high frequency the amplitude will be lower, and you can so this is a straight line. Okay, it is a power law, and to the straight line we need just 2 things. One is the amplitude and one is the spectral index. And for all these 3 time series, if you take the Fourier power spectrum, you will get the same spectral index and same amplitude. So that's why it's called common spectrum red noise process. It's a red noise process in the residual, but for different pulsars they have the common amplitude and common spectral index. And mathematically it can be shown with this, where this is the cross correlated power spectrum in the residual of 2 different pulsars called A and B. Okay, and this is the red noise process where it is the amplitude is AGWB, and this gamma is the spectral index, and F is the frequency. And this capital gamma AB is coming because of this Hillings and Downs correlation. Like if 2 pulsars A and B, then if they are like 0-degree angle between them, then it will be around 0.4, 0.5. If it is like 90-degree angle, then it will be negative minus 0.2. Okay. Yeah, it depends on the position. Yeah, it is the correlation coefficient. Yes. Yeah. And what have we found? Okay. So here I am showing how the posterior distribution. Posterior distribution means like what is the probability of having different values of this gamma or the amplitude. Okay. And this is a 2D probability distribution. You can think like this. And this is the posterior distribution of this amplitude and the gamma that we have detected, like at different PTA. For example, the orange one is what Nanograv have found. The blue one is what EPTA and NPTA have found, and the green one is what pulsar timing, Sparks pulsar timing array has found. Okay, and if you combine all of them together, then you will get something like this black contour. Okay, this is the probability distribution.
So index of the power spectrum.
Yes, the spectral index of the power spectrum at 1/year. 1/year, 1 year. Yes, because we are talking about nanohertz, right? So yeah, 1/year is like roughly 80 nanohertz. I don't know. Yeah.
So the best one is what, 3.5, the spectral index.
Yeah, it peaks around 3.2 or 3.3, I think.
Is that theoretical?
I'll come to that. Yes. And the amplitude is around minus 14.5. Okay, amplitude of the those are strain. This is the gravitational strain or gravitational amplitude. And but this is not enough, right? Have we found the Hillings and Downs correlation? Okay, because without the Hillings and Downs correlation, these things can happen for like from something else also. And again, here I'm showing what the Nanograv has found. Okay, so again, the x-axis is the angular separation between pulsars, and y-axis is the correlation. And this purple curve is what we expect from theory. If there is isotropic background, then this is how the correlation should be. And these blue points with the error bars, this is what we have detected from our data. Okay, so you can see, although like for now the error bars are sort of largest, but still it is following the pattern of the Hillings and Downs correlation. Okay, and if you calculate what is the significance of detecting this Hillings and Downs correlation, it's around 3 to 4 sigma for different PTAs. Yeah, I mean, if you do the mathematics, it will turn out with 2 sigma. Yes.
So you can go to pretty high sigma even with this video.
Yes.
It was definitely seem like it looks 3 for sigma because there is beam to beam correlation.
So
Then you can
I can discuss in more detail how the distance significance calculate later.
I believe it's almost like I can feel a straight line. Right?
that's what you
But, but yeah, if you have many data points, then that's
Okay. How much time do I have?
you have about
15 minutes.
yeah.
Okay. So now, what is the source of this background in this, like that we have found the evidence for? Okay, and the most interesting source or the most promising source for the background is inspiraling supermassive black hole binaries. Okay, so we know almost all galaxies have a supermassive black hole at their center, and we know galaxy merger is also pretty common in our universe. So when two galaxies merge, it is inevitable like the two black holes at the center will come to the merger at the center of the merger product, and at some point they will form a bound binary. Okay, and so supermassive black hole binary, if you take this formula, if you have a total mass of around 10 to the 9 solar mass, and if the separation is around 10 milliparsec, then the orbital frequency will be in the around 10 nanohertz. Okay, and for circular orbit, if the orbital frequency is 10 nanohertz, then the gravitational frequency will be twice of that, which will be 20 nanohertz. So that falls in the frequency range of the pulsar timing array.
-3, -4 nanohertz.
Oh, the high it can go? Oh, nanohertz?
How low?
How low? It can go very low, but at very low frequency, the amplitude also be very, very small. So when you are very far away, so the orbital period is let's say 1000 years, then it will be like picohertz. But when they are that far away, the gravitational wave that are emitting will be very, very weak. Same thing for LIGO. In LIGO only we detect the last part of the merger.
Acoustic background
Yes.
can come from other thing also.
Yes.
So that can be very low.
Oh, you think like with the experiment, how low we can go? Okay, with the experiment, how low we can go depends on our data span. Okay, if our data span is 20 years, then the lowest frequency we can get is 1/20 year. So we have to convert that in nanohertz. Yes, it's just coming from like if you do a Fourier analysis, a Fourier transform. This is
In nanohertz. Yes.
20 nano is like
1 year is 10 to the minus 7 hertz.
yes.
So that's 100 nanohertz. So 20 years.
It's like 3 times 10 to the 7, so it will be around 2 nanohertz. Yeah. So 20 is around 2 nanohertz. That is the lowest we can go for now. But I mean, if we have 100 years of data, then it will be like maybe a little lower than 1 nanohertz. So as we have more and more data, the lower frequency limit that we can explore will be go lower, down and down. No, LISA is in a millihertz. Yes. So at higher frequencies. This is nanohertz. So this is till now this is the lowest frequency, but
Yeah.
So I can understand why the time is figuring out what is the threshold of the experiment's sensitivity. Because I was assuming that the distance between the pulsars should be the limiting factor. So because the sensitivity towards the gravitational waves frequency will depend on how far the or what is the span, the distance between the pulsars are.
okay. In the case of PTA, what as I said, that for the background, it will it will come as a like red noise process. Okay, and let's say if you have a time domain, decision time domain, and if you want to take a Fourier spectrum or Fourier transform, if you, it's just from coming from the like if you take any Fourier transform any time series, the lowest frequency information that you can get is 1/T. If we have this, for example, yeah.
So I think my Monica's question is that you have a fixed, if I understand this question, that you have a fixed array of pulsars. These pulsars are pretty fixed.
Yes.
So and they have some time period, and if there are gravitational waves coming, then there will be this difference in the time period, and you can look from angular correlation of this difference in the time period
Yes.
of the millisecond pulsars. So his question is that why would that signal get better, or why can we reach lower and lower frequency?
You can reach sensitivities, I can understand. With,
The amplitude, in the
Yeah.
amplitude, like you have more and more data and the amplitude. But why would that go to lower frequencies? Because frequency is pretty much governed by what is the distance scale between the pulsar systems.
That is true. Okay, so for example, okay, let me then explain this. For pulsar, when you observe this, the distance of the pulsars are actually much larger than the wavelength or gravitational waves. Okay, so what we're doing here, so then again I have to come to explain this. Okay, so let's say I can draw here. Let's say this is a pulsar, okay, and this is the Earth, okay, and the gravitational is coming. It is like far enough that we can think of as a linear waveform, and the wavelength of the gravitational wave is actually like something like this. Okay, so there are multiple wavelengths of gravitational waves that is happening between the Earth and pulsar, and what we are measuring is actually time delay. So what happens? So what is this gravitational wave doing? Okay, it is changing the curvature in the space time. Okay, with the curvature is changing this, it is changing the gravitational potential. Okay, and we know if we go to higher potential, then the time will go slower, and if we go to lower potential, the time will go faster. Okay, so let's say what happens is at the position of pulsar, there is a particular strength of the gravitational wave. Let's call it HP. Okay, and so what is happening? Like at that time, when a pulse is emitted, the rotation of the pulsar, the time, okay, it will depend on HP, because if it is HP is low, the time will be different compared to if the HP is high. Okay, similar at the same time, okay, at arc also, because of this background, okay, here we have also like effective gravitational strength, we call it HE. Okay, so what is happening ultimately is when a pulse is emitted here, it has a like particular H, which is HP, and it is, let's say there's, if we call it as like sine wave, and it is going up down, so it is like getting red shifted and blue shifted, and ultimately coming to Earth, and again at a particular HE. So what will ultimately determine the change in the time period is HE minus HP, because whatever happening inside is get integrated out. Okay, so in that sense we're actually measuring the time delay. Okay, if the gravitational wave curvature, it is creating a higher potential, then the pulsar will slow down comparatively when this is like lower potential, and it's some like gravitational red shift. Okay, like from Earth, yeah, if we like put a laser light, if we go higher, it will be like red shifted, because it has to go through some gravitational potential. Okay, so here the length scale doesn't matter, because ultimately what we are measuring is what is the strength at Earth minus what is the strength at pulsar, strain and pulsar, and it can be many wavelengths, it doesn't matter. Okay, and as ultimately it will like look in a residual as a red noise. Okay, and as any red noise, like for example, so red noise is again if you take a Fourier spectrum, let's say this is your data span. Okay, let's say this is your data span from 0 to let's say 1 year. Okay, and in Fourier spectrum, what we do actually, we measure the power at different harmonics, right? So at 1 year, if you have a sine wave with a period of 1 year, then this is how it looks. Okay, and we can actually measure the amplitude of the sine wave. But let's see a sine wave of, so this is your data. Okay, you only have data up to this. Let's say now you have a sine wave of 5 years. Then with 5 years, the sine wave will go like this. Okay, and we don't have enough data to measure the amplitude of that sine wave. Okay, so this is basic Fourier analysis.
Okay, I think.
Just quickly, can I just follow up with the question? I know it's very making it very lethargic, but for example, in LIGO, the sense, the frequency sensitivity, that what frequency of gravitational waves we can determine, is kind of determined by the LIGO arms.
Yes.
I think that's what the confusion is. That there you are looking at these LIGO arms, and the size of the arms is kind of determining what is your sensitivity of the frequency, which is lower frequency in case of LISA.
LISA, yes.
Arms.
Yes.
So the understanding was that for a pulsar timing array, although there the process is very different, because here you are looking at change of the arm length, the strength
Yes.
in space, whereas here you are looking at the time dilation or time gravitational
Yes.
redshift kind of thing. But yeah, I was still not convinced that I still didn't understand. I'm sure you were saying I didn't understand that if there is a system of pulsars that are fixed, and if I look at it for longer and longer year, why would I?
I think it's the both ways. One is the length scale of
That is
pulsar,
fixing.
one
That's
is
the nanoscale. That's what
nanoscale,
I'm
one fixing, and then also since you are doing the Fourier transform of it to get the power spectrum, that is taking your the actual data timing, which you
So I
are
guess the
observing.
question is with LIGO,
Yeah.
if we observe for
Yeah.
years and years,
So
it's not like we'll get other frequencies.
One is the length
no, I don't
constraint.
think if you look at LIGO for years and years and years, that won't change your frequency sensitivity curve.
It is within the frequency sensitivity right now.
How
for
much can you
data,
approach?
how much
So
you
I
can
think
go.
then the understanding is that in the pulsar time configuration, there is a range of
Range.
frequency. To probe to the lower end, you have to do longer
You have to do
time.
longer time.
Yeah, I mean, this is what we have a like sensitivity curve
So that
for
is
PTA.
within the- got it. Yes, please.
Okay.
Sorry, yeah, sorry for the
Please
discussion.
go ahead, yes.
Okay. So yeah, the most promising source is supermassive black hole binaries. Okay, and from theory, if we have a population of supermassive black hole binaries, then actually we can calculate what the gamma should be. Okay, and just from theory, the gamma turns out to be 4.33. Okay, but in this theory, it assumes the two supermassive black holes are just there. There is no other environmental effects. There is no like other stellar environment or circumbinary disk or accretion disk, and the inspiral or the gravitational is totally defined by the emission of gravitational waves. Okay, in only that case it should be 4.33. But if there are like surrounding effects like accretion disk, circumbinary disks, and other things, then they will also affect the gamma, and they can push the gamma towards a lower value. Okay, and so yeah, this black dotted line shows this 4.33 value. But what I have found is this, right? So now we think, although the posterior distribution is consistent with 4.33, but it's like the peak is towards lower value. So we expect these black holes that is emitting the gravitational waves, what we are detecting, is most probably like not sitting there in an empty space. There are environment around them, like probably circumbinary disks or accretion disk and so on, which is affecting the spectral index. But the supermassive black hole binaries, although these are the most promising, they are not the only source. Okay, there are other proposed sources, the cosmological sources. They can also create nanohertz gravitational waves. Okay, and I don't exactly know how exactly they will do it. Okay, but I know people have said this can do it, like for example, cosmic strings, inflation, cosmological phase transition, and there are more things. Okay.
These are all fantasy.
These are fantastic.
Yeah, this transition is not, but yeah, but I think I think these you know the amplitude from these all, even if they exist, the amplitudes will be much less than what you would expect from supermassive largest.
So I think there are enough freedom, or like there are enough free parameters that they can fit. Yeah. Yeah, so they can match this amplitude also. Now, how much would we believe them? That I don't know. Yeah, but what can I do to say no? The background, what is we are saying, is actually from supermassive black hole binaries and not this cosmological things. Is right?
All this, but
Yes.
So I have no knowledge about this field, but from what I have read and understood, it has to be majorly supermassive black hole margins.
Yeah, that's also most of us what think that. Yes. But one way is to confirm that is, okay, so what are the next steps? Okay, the next step is to get a like more significant detection, like because 5 sigma is sort of like the untold threshold to confirm anything. Okay, and of course get a more precise measurement of the amplitude and the spectral index to know more about what is happening with the supermassive black holes. But still, like even if we have more precise measurement of A and gamma, still we cannot say whether that it is not coming from cosmology, because they have enough freedom, they can also match that. Okay, so one like thing we can do is, like if we can detect gravitational wave from an individual supermassive black hole binary, okay, the continuous waves, then we can say at least some part of it is coming, the background is from supermassive black hole binary. And we can do that because why? From theory we expect this is how a supermassive black hole binary population will look like in terms of like frequency and strength, and all of them together will create this background. But there must be some sources which may be like more massive or nearby, so that they will like stay above the background, and we should be able to detect continuous gravitational waves from those sources on top of the background. Okay, and if we can do that, then we can say for sure, like yeah, the background, at least some part of it is coming from the supermassive black hole binaries, and then we can do like more like population study of supermassive black hole to match whether the amplitude is exactly matching with what we expect. Then we can say how much, what fraction of the background is from supermassive black hole binaries. And another thing, if we can observe the supermassive black hole binaries both in gravitational waves and also in EM waves, then we can observe the same binary in both these messengers, and we can start multi-messenger nanohertz gravitational astronomy. And as like any multi-messenger observation, the multi-messenger observation of nanohertz gravitational waves will also answer lots of questions, like how do supermassive black hole binaries forms and evolve. One thing is the final parsec problem, although nowadays there are lots of mechanisms proposed that can work on the final parsec problem, but there is, we don't know for sure which one it is, or like whether there are multiple channels. What are the EM signature of binaries? For example, if a galaxy or a AGN has two black holes orbiting around each other in the center instead of one, then in the EM light curve we should see some signatures. Okay, or also in like either spectroscope we can also have signatures, which is a periodic variation. So if we have one detection, we'll know for sure how they should look like. We can also learn a lot of other things, like how galaxy mergers shape the galaxy formation evolution, in that how do supermassive black hole growth, and we can even for the multi-messenger supermassive black hole binary observation, we can also do the measurement of Hubble constant. But easier said than done. Okay, there are lots of hurdles how to go ahead with that, and there are three main things that we need to take care of. And among these three major things, this is the things I personally work on. One thing is developing accurate and efficient pipelines to search for continuous waves in PTA data, because nowadays it's all fitting model to a data. Okay, and for PTA our data volume is huge. Okay, we have like millions of TOS from multiple pulsars observed with different telescopes, and so like finding a, and also the whatever we're detecting, they have multiple components. Okay, like we have background, we have pulsar noise, on top of that we have to find this continuous wave. Okay, so yeah, what I'm doing is I'm developing the pipeline for searching for eccentric supermassive black hole binaries, because till now most searches has been done with circular, but we expect supermassive black hole binary should be an eccentric orbit. Yeah, so I'm developing that. So if you have if you're interested in that, you can talk. Another thing is identification and in-depth study of supermassive black hole binaries using electromagnetic observation. There are a couple of sources which are particularly interesting to me. One is OD27, which I have worked a lot during my PhD. And one recently I have started working is TikTok, which was supposed to be like a very like close to merger black hole, which should merge within 3 to 4 years. But probably now we know it's not probably a black hole binary candidate. It was like a false alarm. And last but not the least, we need high quality data. Okay, and to get high quality data, we need better polarization calibration, which I have done worked on of the pulsar profiles. And through IPTA, we should combine data from different PTAs to form a bigger data, usually more sensitive. And currently, the work is in progress to combine data from different PTAs to form the third data release of IPTA DR3. And the data release and the results should be coming within next 2 to 3 years. And another thing is understanding noise, which is coming from ISM and solar wind. Okay, I will not. I am not aiming to go through all of them, but I will just go to the summary at the end. Yeah. So how does the future roadmap look like? Okay. So this is what we expect in an ideal case. Okay, but there can be deviations because we don't know what realization of universe we are living in. Okay. So ideally, we should expect a 5 sigma detection of the gravitational background within 1 to 4 years, and a EM detection of supermassive black hole binaries. Although now we already have lots of candidates for supermassive black hole binaries, but with LSST becoming online, it will observe millions of AGNs, and we have a good light curve of them. So within 2 to 10 years, we should detect more EM candidates of supermassive black hole binaries, and yeah, within 3 to 6 years, we should have a detection of continuous wave from an individual supermassive black hole binary, and probably within 5 to 8 years, we have the multi-messenger, like observing the gravitational waves and also the EM wavelength from the same source. And yeah, in 2034, the LISA will fly, so we'll start the millihertz gravitational waves. So with that, I'll just leave my conclusion side, and thank you.
Okay, questions, comments? Yes, Siddhartha?
In case a gravitational wave is detected, and as well as neutrinos are detected from the same direction. So in that case, does it like ice cube confirms that the neutrino is detected, or like GW has some other kind of detection process?
Till now, we don't have any detection of gravitational wave and neutrinos from the same source. But it is possible, like when two neutrons merges, in principle, you should have gravitational waves and neutrinos and electromagnetic. So yeah, ice cube may detect gravitational waves from them.
Sources, they have confirmed it.
Okay.
But in 2019, 2018, 2019, ice cube and this LIGO.
Okay.
But this gamma and gravitational,
that is confirmed. Okay. Yeah, so there is no confirmed simultaneous detection of neutrinos and gravitational waves as of now.
Because the galaxy objects, there has been a lot of studies, like not a lot of, but there has been significant studies, and there has not been any significant detection of neutrinos, like
from galaxy mergers.
From high significance, I think so.
Galaxy mergers you're talking about?
Or neutron star mergers.
The processes. I mean, the Milky Way neutrinos were only detected like.
Yeah, but
I
there
think 3 years
are
back.
4 possible PV neutrinos that has been
Ultra-energy neutrinos.
AGN. That is maybe extragalactic.
Yeah, extragalactic and AGN is one type.
Yeah, maybe they are kind of blazars, like is one of the possible sources. Yes.
Questions?
Yes.
First of all, nice talk. I just want to say that I'm asking you earlier about the mass range of the system.
Yes.
You said it will be on the order of 10 to the 8, 9, 10, etc. Now 10 to the 8 and with the mass ratio 10 to the minus 4, it can be also observable by the LISA. So LISA is observing the inspiral phase.
Okay.
So PTA is also observing the inspiral phase, or it can observe up to 9.
No, PTA, with PTA we can only observe the inspiral phase. Yeah. Yeah. With LISA, maybe we can observe merger of sort of less massive, like 10 to the 6 solar mass.
With the LISA. I mean, for the stellar black hole binaries, we can observe their inspiral phase through LISA.
Yes, true.
But, yeah.
So
here it is, these are both supermassive, right? You are talking about
MD,
the extreme ratios, where you have a stellar mass kind of black hole and a supermassive black hole. But for both supermassive, then the frequency will be low.
Yeah, low. That means you are observing with PTA the intermediate mass supermassive.
no, we are observing massive, supermassive, both of them.
Intermediate, yes. Ratio is yes.
Oh, the ratio.
Yeah.
Oh, the ratio is like, again, the mass ratio will also depend the strength of the binary. Okay. If they are like close to equal mass, then it will be more like strength will be larger. If the mass ratio is very small, then the strength of the gravitational emitted, the amplitude will be also very small. Okay, so if the mass ratio is also very small, then we just from the amplitude perspective, we should not be able to detect it with PTAs as of now. Maybe as we have more and more sensitive data, maybe yes, but for now we are thinking like mass ratio of 0.01 at the lowest.
That means.
Okay, yeah. I don't know like what is called intermediate, what is called high. Okay. Okay.
Anything above that is intermediate.
Oh, so then intermediate, yes. In terms of mass ratio, we're intermediate. But in the total mass, it's supermassive.
So the point is there is some overlap between these detectors based on what kind of binary you are.
That means we can also do the same system by PTA and also by LISA and also by LIGO, depending on.
No, can LIGO and PTA have overlap?
No. LIGO cannot. LISA and LIGO can have. Even PTA and LISA can have overlap, some overlap. Because based on at what stage they are.
What kind of
Other questions? Okay, sister.
since you have detected a background, and if you say that it is only due to the supermassive thing,
Yes.
we can say that what is the population of it?
Yes.
And what is that and how that correlates with other known observation?
Yeah, I mean, as of now, as you can see, like the posterior distribution is very wide.
No, I'm not.
Okay.
I know the amplitude roughly.
Yeah, the amplitude also, the range is pretty large for now. Like it can go from -15.5 to -13.5. Yeah.
Okay.
But as we have more like stricter constant on this, already people have done studies on this. Okay, like they compare this amplitude and spectral index with the population model. Okay, they do the simulations, and as I said, like just from the spectral index being little lower, we are saying like the supermassive black hole binaries have some environmental effect that is affecting the spectral index.
No, I'm just
The amplitude.
Take the amplitude.
Yes.
What is the number of binaries required to produce that right?
Yeah, there have been studies like that. Yes.
And how does it compare with?
So do you have any sense of an approximate number from the number of such binary candidates that can produce this kind of a background level?
I think there is a like population distribution that people have proposed, but I am not very familiar with it. Yeah, but maybe I can take a look.
That is a very valid question because people have been trying to look for SMBH binaries and mergers in the electromagnetic window for the last 15 years at least.
Yes.
So apart from like a handful of sort of double emission lines, etc. I mean, this from the theory of galaxy formation and evolution, these should be everywhere.
Yes.
But electromagnetic window hasn't been able to find these things. So that given that there are so many, I mean, some amount is being predicted from the background, the stochastic background. So that can inform the electromagnetic window. But what should we look for?
Yeah, I think people have done it other way around. Like people have looked at the galaxy catalog and galaxy merger rates and tried to predict what the amplitude of the background will be. And there are like huge range on that. Okay, like different studies depending on what kind of assumptions you take and what kind of like correlation you take. The range can be go from like -18 to -14. Okay, for the amplitude. Yeah. So just from that, we can actually say some of the studies are not valid because some of them predict also like -18. So as I detected like around -14.5, so we can say okay, those population models are wrong. Okay. But even on those population models, there are uncertainties. Here also in the detection, we have uncertainties. So as of now, it's we cannot pinpoint exactly how many numbers are there.
No, I mean, if you take the higher level.
Oh, okay. We can put an upper limit.
Upper limit or lower limit.
I think this actually, I don't know, but my speculation is the upper limit of this is actually overshooting the current electromagnetic limit.
Yes.
we should see more in the electromagnetic band.
Electromagnetic.
Yes.
Yeah, I think it's a very much related question and it has two parts. The first part is that when you, as you said, when you are talking about the amplitude,
Yes.
that should put some constraint on, as you say, population models, right?
Yes.
And these are all integrated signals, so this would be like supermassive black holes that have happened, all through the time of the universe, because these are all integrated.
Yes.
signals.
Yes.
So one thing I'm just curious is people run cosmological simulations,
Yes.
right? So you are actually simulating the universe, and they are although crude and not accurate, but people do have supermassive mergers. The supermassive black holes merging.
Yeah.
That is always being done in
Cosmological simulations.
So was there any study to try to use the the ITTA constraints
Okay.
to see that actually has anything to do with what is the prediction from this in-body or hydrodynamic cosmological simulations on what could be the SMPH merger rate. So this was a discussion I had like 10 years back with my
Okay.
Yeah, you have some way to merge the black holes. They have to merge the black holes.
You were talking about the margin and parsec, less than parsec.
Yes,
Where
but
you are seeing the inspiral.
That's right,
That's
but
not,
this is-
that's not what you need. You just
You just
need
need
that
the
how
rate.
many there will be at a
The rate,
given
the rate.
volume.
the rate. Because eventually
No,
they will merge.
when you go to that,
So
You
the
don't have
point
to
is,
go.
the point is that eventually they will merge. And whatever physics happens in the parsec or
that I
sub-parsec scales,
understand.
we don't care. But as long as in your cosmological simulations, you come within the splitting length or the gravitational softening length, you merge the two black holes. So I'm talking about the rate of mergers. Can we have some constraint on the rate of mergers?
Yes, as I already said, like people have lots of different models, and based on that model, they have predictions on the amplitude. Okay, and so what people have done, because those predictions have been done before the discovery or of the detection, and then from this we have compared like what those have predicted and what we have found. Okay, and there is a huge overlap for most of those models with this posterior distribution, except like 2 or 3 of them. Yeah.
Second part of the question is that when you talk about this gamma, the
Spectral index.
Spectral index, how was that determined? Like, how do you get this?
The 4.33. Okay, the 4.33 doesn't depend on population or anything. It just depends on how fast the binaries evolve. Okay, so just from them, like just from how fast it evolves, you can actually get some estimates like at each frequency bin, how many of them are there.
How fast they can evolve?
Yes,
Will depend on their mass, right?
will depend on their mass. Yes.
There must be some underlying mass distribution.
No, to get the gamma, we don't need any mass distribution. It's just, so gamma means at what frequency, relatively how much power will be there. Okay, and so whether it is massive or less massive, all of them will go through the frequencies.
It's effectively the time scale of merging in some sense.
Yes.
But when you are saying that this is the spectral index, so this is
Yes,
giving
time
us,
scale.
we are giving
Time
the
scale
time
is
scale of merging, and so like so yes, please go ahead. Sorry.
Yeah. So just like if we assume just the inspiral is happening due to gravitational emission, okay, and nothing else, then we know how the frequencies will evolve. Okay.
The time scale.
Time scale. Yes. Now, if there is some surrounding things that is affecting the evolution, then
That can change.
that can
But
change.
let's see the stellar mass black.
Okay.
What
Oh
is
yeah. I mean,
that?
yeah. So there is some mass like saying, okay, this is around 10 to the 9 solar mass. Yes. Okay. Yes. So this is for supermassive black hole binaries. I am not sure because LIGO is also trying to detect the background,
Yes.
so they must have something.
Yeah.
Yes. Yes. But yeah, I don't know for sure. Yes.
Depends on the mass population, mass spectra, and the integrality, how fast it is merged.
Yes. So the mass spectra has to be somehow there. Right?
So for LIGO and for PTA, is the redshift of the system, the binary, does it affect the detection similarly?
Yes.
The same.
Yeah.
same kind?
Yeah. because the amplitude falls as